All right, we just finished talking about standard deviation, and I want us to make sure that we talk about the term variance as well. Sometimes you'll hear textbooks or myself talk about variance, and the variance and the standard deviation are related, closely related. The variance is just the standard deviation squared, and so sometimes you will need to know that relationship. So if you're given the standard deviation, you can just square it to find the variance. And vice versa, if you're given the variance, you can take the square root of it to get the standard deviation. Okay, so next thing that we're going to move into is just a reminder about the different descriptive measures for populations versus for samples. So we learned way back the first week of class that if we find a descriptive measure, so something like a mean, so a measure of center, a measure of spread, like standard deviation, if we find one of those descriptive measures for a population, that is called a parameter. And parameters are fixed, they're constant. Once we know the population, then the mean doesn't change, the median doesn't change, the standard deviation doesn't change. Statistics, on the other hand, these are descriptive measures for the sample, so like the mean of a sample or the standard deviation of a sample. Those change, right? If I took a different sample, I might get a different sample mean, so a different estimate of the true population mean. If I took a different sample, I might get a different standard deviation. And so we want to make sure we understand that parameters are fixed, but statistics are going to be varied, so they're variables. We have next just a quick summary of, I guess, in comparison of the terms and formulas used for calculating both mean and standard deviation from either a sample or a whole population. So this first column here, we are just specifically looking at sample data. So we don't look at the whole population of interest, we take a sample from the population. We would calculate a sample mean X bar by adding up all the data values and dividing by how many there were. And we would take a sample standard deviation using this formula, and we just did an example of that in the last video. If, on the other hand, we have data from an entire population, this is going to be really unusual. Very infrequently do we have data on an entire population, but if we did, we would calculate the population mean, mu, by adding up all the data values and dividing by n. We would calculate the population standard deviation using this formula. It looks really similar to this one, but you'll notice the denominator changes. So instead of using the sample size minus 1, which we did for a sample, we use the entire population size. We do not use the minus 1, okay? And we look at the deviation of each x value from its population mean rather than the deviation of each x value from its sample mean, okay? So this next example down here, we're going to do this using the calculator, but I just want us to pay attention to the different outputs in the calculator. So this says the values below represent the number of points scored per game for every game in the Arizona Cardinals 2015 season. Use your calculator to find the population standard deviation. So we didn't take a sample of games from that season. We took every single game score from that season. Or I guess not score, but number of points scored by the Cardinals. And so this is going to be a population standard deviation. If we look back up here under standard deviation, this is not a sample standard deviation S. This is a population standard deviation sigma. Okay, so we need to find sigma. The way that we're going to do that is we're going to go back to our calculators here. We're going to input all of our data. So we're going to hit Stat, Edit, and I'm just going to clear what I had in list 1, and we're going to put in these scores. So we have 31, 48, 47, 22, 42, 13, 26, 34, 39, 34, 19, 27, 23, 40, 38, 6, 26, and 15. So we had 18 total games. We entered the score for each of those games, and then we're gonna hit stat. We're gonna scroll over to calculate, and we're still gonna choose one variable, stats. We were using list 1, so I'm changing this here to say list 1. We were using list 1 because that's where we entered all those scores. And you can tell it gives you X bar, so the sample mean, if this was from a sample. It gives you S sub X, so the sample standard deviation if this was from a sample, and sigma sub X, the population standard deviation if this was from a population. So what we have to understand here is that the calculator is only doing what you tell it, and the calculator does not know whether this data set that you just entered was a sample and it should calculate S, or a population and it should calculate sigma. So it's giving you both, and you need to decide which one is correct. In this case, because we were asked to find population, we should have been using this formula, which is going to give you a slightly different value than if you used the sample formula. And so we get a standard deviation for the population of 11.53 if we round there to 2 decimal places. And an interpretation of that means that on average, the number of points scored per game by the Cardinals in 2015 varies from the mean of, and we have the mean, right, 29.4 by 11.53 points. Okay, so the average distance of each observation from the mean. Okay, so the main thing there I just wanted you to make sure to get is that we have different notation for sample mean and population mean, and different notation for sample standard deviation and population standard deviation. That is going to be really important as we move to the rest of the content in the course. Okay, so one last thing that we're going to cover in this chapter is one of the uses of standard deviation. And one of the things that we do with standard deviation is we use it to determine whether or not a particular data value is unusual and how unusual it is. So if a data value is within 2 standard deviations of its mean, okay, so I should put that in there. If a data value is within 2 standard deviations of the mean, then that value is, we would say, a fairly common data value. And if the data value is outside 2 standard deviations from the mean, either above or below, then we would say that observation is uncommon or unusual. Okay, so an easy way to figure out how many standard deviations away from the mean an observation lies is to use this formula. And this formula is actually going to be something we use again later that looks like this, calling that a z value. But for now, we're just going to look at the process of taking an observed value, subtracting its mean, and then dividing by its standard deviation. So this example says, suppose a passage of play in a rugby game takes 75.1 seconds. Would it be unusual for this to happen? Use the population mean. So population mean is telling us mu of 32.1 seconds. And standard deviation, again, it's telling you from the population. So the population mean and standard deviation, that means that sigma is 18.5. And so what we want to know is, well, what about this particular value of x? Is that normal or is that unusual? So x is the 75.1. So I'm going to plug it in there. Remember, we're doing x minus mu over sigma. So I have x minus the mean was 32.1. The standard deviation was 18.5. So if we take this difference in the numerator here, 75.1 minus 32.1, 75.1 minus 32.1, we get 43. Okay, those units are seconds, right? So what we know is if I take the difference between 75.1 seconds and 32.1 seconds, I get 43 seconds. So what we just determined is that this particular rugby play was 43 seconds longer than the average, right? This one was 43 seconds longer than the average, longer because it was positive. And now we want to know, well, how many standard deviations is that? Remember, standard deviation has the same units as the original variable. And so these seconds are going to cancel. And what we're saying is, how many times does this standard deviation of 18.5 go into 43? So how many of those standard deviations go into 43? So 43 divided by 18.5 is 2.32 times, right? About 2.32 copies of 18.5 is what it takes me to get to 43. These units are standard deviations. So what we're saying is that a rugby play lasting 75.1 seconds is 2.32 standard deviations above average, right? Or above the mean. And so it takes 2.32 copies of that standard deviation 18.5 added to the mean to get us to that score of 75.1. And so if we were trying to determine if that's unusual, remember what we said above is that if a data value, so if an x value is within 2 standard deviations, so if this score was like a 1.32 instead, right? If it's within 2 standard deviations, then it's fairly common. But if it is more than 2 standard deviations away from the mean, either above or below, so either a positive or a negative value here, that's 2 or greater, or -2 or smaller, then we would say it was uncommon or unusual. So in this case, we would say this is an unusually long, because it was bigger, right, above average. This is an unusually long play.